Yeah, Kalyan, please send the WhatsApp message. Only 25 students are there. Please send me a reminder to all your your students, your friends, please. Are you able to see my screen? PPT? Guys, please someone reflect.
No, sir, you're not presenting your screen.
Oh. Now are you able to see?
Yes, sir, now it's visible.
Okay guys, very good morning. Now today we are going to discuss the problems which concept we discussed in the last classes. I mean previous classes we discussed the welded joint, okay? The concepts of welded joints, different concept and different load condition we discussed. So today we are going to discuss the corresponding problems, okay? Now the first problem anyway, I mean just a recap, just 1 or 2 minutes, because the students in between time they may join, so just we go for the recap and come for the problem. Okay, I mean these are the things we discussed in the last class. The strength of the parallel flat weld. Parallel flat weld, see here, that is here that I mean shear stress in the parallel flat weld, tau is equal to P by 0.707 HL. H is nothing but leg of the weld. L is length of the weld. These are the things you have to keep in mind. Okay, P is nothing but, I mean, tensile force on the plates, right? These are the things. And this is the strength of the transverse flat weld. I mean, in parallel flat weld, the weld is subjected to shear. I mean, transverse flat weld, the weld is subjected to tensile stress, or weld is subjected to tensile stress. Very important. This kind of questions you may expect in your competitive exam and even your objective also. Okay, now sigma T is equal to P by TL, P by 0.707 HL, H is leg length. Okay, that's, and L is length of the weld. Now maximum shear stress in parallel flat weld, I mean we have discussed and we came to know that theta is equal to 45 degree. I mean when the weld is the weld at the, I mean we are considering this a triangle's cross section of the weld. There are two type we discuss. I mean circular shape weld and triangular shape weld. This weld is better than our convex with under circular shape weld. When we are filling the material, it will be going to be formed these two type. Now actually we are considering only triangle shape weld only. Okay, I am talking about this one. Just I show you and come back again. I am talking about this convex and normal. We are considering normal. The normal weld is better than convex shape weld. Okay, that's what I am telling here. Anyway, now this is the maximum shear stress in the parallel flat weld. The theta is equal to 45 degree. Then tau max is equal to P by 0.707 HL. Okay, I mean anyway we discussed previously the strength of the parallel flat weld. During that time we assumed that 0.707 P by 0.707 HL. Now we have been proved here, that is tau is equal to tau max, here P by 0.707 HL. That's all. Then maximum shear in transverse flat weld. Here also we have been proved. I mean 67.5 degree. 67.5 degree. Now, I mean now that the transverse flat weld strength is 1.17 times transverse fillet weld strength is 1.17 times of the parallel fillet weld. But even though if for safer side, safe design applications, we are considering, the theta is equal to, mostly we are considering theta is equal to 45 degree, both the transverse fillet weld and parallel fillet weld. Now later we discuss axially loaded unsymmetrical welded joints, right? Now this here the top and bottom welds. Here the top and bottom welds, this is the top W1, W2 are unequal length. The weld lengths are unequal, hence we are calling this unsymmetrical welded joints. Then corresponding load, what is the load here? P1, P2, corresponding weld to P1, corresponding weld to P2. How do I find out the P1, P2, and how do I find out the weld length? We discussed in the last class. L1 Y1 is equal to L2 Y2. L plus L1 plus L2 is equal to L. From these relations, we are able to find out, our length of the weld 1, length of the weld 2. That's what we discussed. Now, later we discuss the eccentric load in plane of welds. In the plane of welds. Okay, eccentric load in the plane of welds. Here, very, very important problem. This one very important concept. We are going to discuss most of the problems based on this concept only, because previous concepts, direct formula substitutions, you can practice yourself. It won't be a complicated problems. Whatever we discussed earlier concept. This is a concept, important concept. We are going to discuss the problems today. Tau 1 is equal to P by A. This is a direct shear. This is nothing but a bolted joint and riveted joint. When the bolted joint and riveted joint load is acting in opposite distance, eccentric distance from the bracket or frame. Hence, the bolted joint and riveted joint subjected to primary shear, secondary shear. Similarly, the similar concept here also, because when the load is acting here, eccentric distance from the weld is subjected to direct shear, that is called the primary shear. The weld is subjected to due to torque. Torque here, load into E, that is P into E. Due to that, the shear is going to be subjected, that is called secondary shear stress. From these two shears, we are going to find out the resultant shear. Okay, resultant shear. Now, the very critical thing is here, very important thing is here to find out the moment of inertia. Very, very important parameter to find the moment of inertia. Now, for our discussion earlier discussed, this is a small. We have to find out first common moment of inertia. Then, with respect to each weld, we have to find out the moment of inertia with respect to each weld. Now, this with respect to moment of inertia with respect to weld. So for weld 1, I'm considering any one of the weld, top or bottom. I'm considering weld 1. This is the IXX is equal to LTQ divided by 12. Then the T is very small as compared to length of the weld. Then this is eliminated. But L is, with IYY, TLQ divided by 12. Only I'm considering this. Okay. Now, what is, this is with respect to weld. With respect to weld, the amount of inertia with respect to weld, A L squared, the LTLQ divided by 12, we have been written in terms of area, A L squared divided by 12. Okay. Now, this is our with respect to weld. Now, with the common amount of inertia with respect to the parallel axis theorem. This is a common amount of inertia, center of gravity, common center of gravity. Then parallel, we are using parallel axis theorem. Then JG1 with respect to individual weld plus, common amount of inertia AR1 squared. A is nothing but AR1 squared. JG1 plus AR1 squared. Then sum it both. That is our weld amount of inertia. Then each weld you can do it. J1, J2, J3 like that. Now, this is a very important concept we are going to use to find out our shear stress, resultant shear. Whatever we are finding this shear stress for the particular weld, tau 2 is equal to MR by J is nothing but this one. This one, tau 2. Very important. This one. This is a direct shear, tau 1. Now, based on this, we are going to find out the resultant shear stress later. Now we move to the problem. Now, the first problem. A welded connection as shown in figure 8.2, this is a figure, welded connection figure, okay, is subjected to eccentric force, eccentric force of 7.5 kilonewton. 7.5 kilonewton. Determine the size of the weld if the permissible shear stress for the weld is 100 Newton per mm squared. Here the permissible shear stress they have been given 100 Newton per mm squared. The weld in static condition. Okay. Now primary shear, we know, right? Here the weld, we would like to find out the size of the weld here only. But in the design diagram, they have given weld length is 50 mm. They didn't give weld thickness. Weld thickness they didn't give. Then what is this? Primary shear. Primary shear is nothing but direct shear. Load by area. What is applied load? 7.5 kilonewton. Then 7.5 divided by area of the weld. Area of the weld. This is a total area here. Total area means 2 into 50 into T. This 50 into T for one weld. Then 2 into 2 means here 2 welds are presented. Hence 2 into 50 into T. Then 100 T. The T is unknown value. We are going to find out that only. Okay. Now secondary shear. Coming to secondary shear, then we have to find out our E. Where the E is, what is the eccentric distance? Eccentric distance from the bar, from the frame. You may consider this is frame. This is bracket. Right? Now, the load is acting from the point to bracket frame 100 mm distance. But here, what is the center of gravity? We have to find out, because the two welds are presented. Then we have to find out center of gravity. Then only we are able to find out the correct eccentric distance. Okay. Now, these both welds are symmetrical weld. Both weld lengths are 50 mm length. Hence, the X bar is, hence that you can easily find out our X bar and Y bar. Here, what is the X bar? Please, can you tell me that? What is X bar and Y bar here? X bar, Y bar. In this weld. Symmetric weld. What is X bar, Y bar? Yeah, please tell me, boss. We don't have time. We have to go. What is X bar, Y bar in this weld, in this arrangement, in this design of weld arrangements? Length of the weld 50 mm. Then in between distance of the weld 50 mm vertical distance. What is X bar, Y bar in this case? Hello? Sorry. Yeah, please. What is X bar, Y bar? Hey, right or wrong, you tell me. Open your mouth. Hello? Kalyan. Hey, someone tell that. Because next problem, X bar, Y bar is very important. This type of problems, you may expect even engineering service exams also. It's no doubt. What is X bar, Y bar in this case? Please, someone tell that, then only I can move next. Okay, are you able to hear my voice or not? Hello? Hello? Hey, my voice is audible or not? Yeah, the mic is already working. Hey, are you able to hear my voice? Hello?
Audible, sir.
Okay, then you tell me, but someone tell me that what is x bar y bar in this case? I'm asking very simple question, no? What is x bar y bar?
Sir, coordinates of centroid, sir.
Yeah, here coordinates is given 50-50 bar. See, the coordinates are given, vertical coordinates is the dimensions are given, no? Yeah, please. Yeah, thank you for at least you opened your mouth. This is 50. This is 50. Then what is x bar y bar in this case?
25.
25, 25.
Yeah, that's what I'm asking. Because some gate questions they're given like that diagram, and it's very minimum. It's not a 2 mark questions, even 1 mark question or 0.5 mark. You can immediately have to tell that at eccentric distance and what is the center of gravity at what is the eccentric distance. Straight away you can tell that. I mean, eccentric distance is 125. 125 is the center of gravity here. CG, center of gravity. Okay, anyway. Now in this case, now my center of gravity is here, hence center of gravity is here. So 25, x bar is equal to 25, y bar is equal to 25. Then what is the eccentric distance? 25 plus 100, 125. Now what is the moment here? P in T. This is P in T. Now, yes? Okay.
Sir, there which point is taken as origin, sir?
What, Amma?
Origin, like we wrote the coordinates of centroid as 25, 25, no, sir. Like which point is taken as origin, sir?
I mean, I'm taking welded region because this is the region is fixed region.
Okay, sir. Okay.
I don't mind about this region because here where my weld is located, that is the holding region. Hence, I'm taking. Your question is valid question because you are thinking about why we shouldn't consider in the corner region, right?
Yes, sir. Yes.
No need. Only you have to consider where our a valid question. Where our welded region is located, that region is going to hold our bracket. Hence, I'm considering that only.
Okay, sir. Okay. Thank you.
Okay. Now, see here. Once we have found it E eccentric distance, then P in T we know our moment. Now the distance for the, I mean, come to this figure now. We would like to find out R distance. I mean, same thing. Welded joint, riveted joint, and bolted joint. Where the corners of R is sitting, where these corners of R welded sitting, where this farmost end from the center of gravity. Now this is in this case very simple. We know this distance 25. We know this distance 25. Then we are able to know R value. R value. Okay. Now each weld. Now we already know they came to know that the J1, right? J1 is nothing but L squared A into L squared by 12 into R1 squared. Here R1 is nothing but, I mean, R1 is, 25. R1 is 25 squared. L is length of the weld divided by 12. Length of the weld squared divided by 12 plus 25. Then this is J1. I mean, here two welds are presented. Directly you can take, symmetrical weld 2J1. 2J1. That's all. Now tau 2 is, what is the tau 2? Tau 2 is equal to torsional moment. M is nothing but T into R by J. Now J is nothing but this one. We know that J value. This is J value. Now substitute here, you are going to get, this is our tau 2. Now see a very important thing. Tau 2 is nothing but 397.8. Please come to this figure. This is tau 2 is acting this direction, in the resultant direction. In the resultant direction, in that sense, this is a perpendicular, right? This is a perpendicular. Now my sorry, my direct series here, p tau 1, then plus, that's what we discussed in the earlier derivation, plus this one. Now what is this? Now this is resultant direction. Now this is my resultant direction. Then what is the component of, what is the vertical component and the horizontal component of tau 2? Now, very easy. Now this is the horizontal component, this is vertical component, right? Then what is vertical component? Because this is a two welds are identical and same dimension, and also center of gravity x bar and y bar also same. Hence I can consider, what is this? This is, I can consider this is A, this is A. Then this is, we know very well now. This is, we know tau 2. Tau 2 is equal to square root of A squared plus A squared. Okay. Now what is my A now? Find out A. This is this horizontal component we know. These two horizontal vertical components we know. Then A squared we have to find out. Then now we know this tau 2 397.8. Leave it T. T is a common. Okay. Now find out find out this. Then we can know, we can come to know that A is nothing but 281.3. Here where horizontal component, this is vertical component. Vertical component. Now we have considered all our identical weld, we have considered this one. This also farmost distance from the center of gravity. Okay, now I consider this one. Okay, now this is our tau 2. This is a horizontal component with respect to our resultant tau 2. This is not a total resultant shear. With respect to tau 2, this is 397.8. The 397.8 resolved into vertical shear and horizontal shear. This is horizontal vertical shear. This is horizontal shear. Now see here, already we have, this is shear stress diagram. Shear stress schematic diagram, this one. Okay. Now we know already direct shear in vertical direction. Why vertical direction? Our load is acting horizontal with downward direction. Hence always, one weld, our weld should be opposite, always opposite, vertical direction. Suppose that the load is acting in vertical direction, upward direction, then in the weld direct shear it will be acting in downward direction. Okay. Based on that, now our vertical, this direct shear is acting vertical direction. Plus, now what is the shear now? What is the component now? 75 plus 281, 356. Now this is our total vertical shear. This is our horizontal shear. Now go for finding our total result. Finding the common resultant shear. This resultant shear is with respect to tau 2. With respect to tau 2. Now this is our required resultant, common resultant shear. Common resultant shear or total resultant shear. Okay, this is a common resultant shear. This is, you can consider common resultant shear. This is a perfect word. Okay, now take vertical component. Now 75 plus 281 going to be 356.3, and I come to here. 75 plus 281 is 356.3. Then horizontal component, this is no horizontal shear here, then 281.3. Okay, now 454. Take resultant from this. Then this is our required resultant shear stress, also called common resultant shear. Suppose the load is acting horizontal direction, then what is the shear? This guy going to be eliminated. What is it? Horizontal shear component. Then 281 plus 73. This kind of questions you may get in competitive, even get questions. They will give the directions and another figure they will give the horizontal directions. What is the total resultance here in horizontal directions? What is the total resultance here in vertical direction? I mean, from this relation, we able to find out our common resultance here. Common resultance here is a 454 by T. Then we have already given the value of shear stress, permissible shear stress. Then from this relation, we able to find out our, I mean, thickness of the weld. We able to find out our thickness of the weld. 4.54 mm. We can assume that 5 mm. I think you might have been clear. Okay, I come to the next problem. See here, this is the problem. Yeah, welded connections as shown in figure. This is the given diagram. Is subjected to eccentric load. Is subjected to an eccentric force 60 Newton, 60 Newton, 60 kilonewton. Sorry, in the plane of the welds. Determine the size of the weld. If the permissible shear stress for the given weld is 100 Newton per mm squared. This also assume that static condition. This is the sum little difficult, I mean little critical. It's not a difficult sum. If you understand, very easy. Now, earlier case only presented top weld and bottom weld. But now this is the, I mean, vertical welds also presented. Now this is there are, I mean, welds. Now I am assuming that the welds are W1, W2 or horizontal weld. W1, W2 or horizontal weld. Now, I mean, weld 3, I am assuming that vertical weld. Vertical weld. I mean, here by symmetry of center of gravity, the welds are midway between the horizontal welds. Here, I mean, see here, Y bar is 50. I mean, because, I mean, both welds are identical. W1, W2 identical, hence Y bar is 50. Simply we can evaluate Y bar 50. Now how can I find out X bar here? X bar is little tricky in that sense. You know, right? What is X bar here? X bar is equal to nothing but, right? I mean, X bar is equal to, I mean, each weld we have to consider center of gravity, right? Now 50. This is what is the total distance, total length of the weld. 50 into what is center of gravity here with respect to weld 1 or weld 2. 50 into 50 by 2. 50 into 50 by 2, 25 plus, I mean, this weld I am taking 50 into total length of the weld, 50 into with respect to weld, this weld center of gravity 25, 50 by 2, right? Plus this weld is 100 mm distance, 100 mm length. But what is the center of gravity? We do not know that weld thickness. Hence, we can assume that the thickness is here. We are assuming here. If you want, you can calculate. Doesn't matter. If we are assuming here the weld thickness is less than length of the weld, hence I am putting 0. Then whole divided by, I mean, what is each length of the weld? I mean, 50 plus 100 plus 50. It will give us our X bar. I mean, then finally we came to know that X bar is 25 mm, 12.5 mm, sorry, 12.5 mm. Now we know Y bar, now we know X bar, then we can easily find out our center of gravity later, common center of gravity. Now come to this area of the weld. First we go for the direct shear. Area of the weld is 50 into T, 50 into T. Area of the weld 2 is 50 into T. Area of the weld 3 is 100 into T. Then sum it all, because we need, this is a direct shear is nothing but a P by total area. P by total area is 200 T. Then be able to know that our I mean primary shear. Okay, primary shear is nothing but 300 divided by T. Primary shear is 300 divided by T. Okay, now our concentration is going to be in secondary shear. Secondary shear. Now see here. Anyway, we know that our CG we know that, I mean, we know that X bar and Y bar. Now we don't know that X bar and Y bar. This is now X bar, right? Y bar. Y bar is here. Okay. Now we would like to find out the R1. I mean, this is a corner. This is R. Well, now that is the farmost distance, right? That is farmost distance. Now y bar is nothing but 50. X bar is x bar. X bar is now 12.5. Now what is this distance now? I mean, this distance is nothing but, I mean, now we would like to find out our R, this value from center of gravity, right? From CG, right? Now, I mean, this is nothing but, what is this distance? 50 minus this distance. I'm asking this distance now. This distance. Now that is nothing but 50 minus 12.5 squared. What is y bar? What is this vertical distance? I mean, here 50, here also it's going to be 50. 50, then we able to find out our R value. 50 minus 12.5 square plus 50 square, this is our R value. Now here two welds are presented and unsymmetrical weld, because I mean this is two welds, weld 1 and weld 2 symmetrical, but weld 3 is different length, right? Hence we have to find out the tan theta. Because of that only we are getting, I mean, x bar and y bar is different values, and the welds also, the vertical distance between the welds also different. Suppose the vertical distance between the two welds are 50 mm instead of 100 mm. This is now 100 mm, right? This is now 100 mm. Instead of 100, if it will be a 50, then it will be a symmetrical. Then x bar, y bar, we can easily find it out as I mean like that earlier sum. Now, now this is the offset distance, right? Then we have to find out what is the theta here. This is the theta. At which angle with respect to center of gravity. Now this is a theta. Okay, 53.13. I mean, vertical distance 50 divided by horizontal distance 50 minus 12. This one. Find out this. This is a theta. Okay. I mean, this is therefore the secondary shear stress inclined at 36.87 with the horizontal. Now we have to, once we know that x bar, then we able to find out our E. Here, what is E here? E is nothing but, I mean, 50. I mean, E is nothing but, this is a distance, right? Where E is sitting here. Then this is the, from this distance. Okay, 50 minus 12.5. Our eccentric load is acting here. That is given 150. Then 150 plus 50 minus 12.5. That is our eccentric distance. Load acting in the eccentric distance is 187.5 mm. From this, we are able to find out our moment. Then now see here, G1, G2 are the center of gravity of the three wells. G1, G2 are the center of gravity of the three wells. G1, G2 here, see here, G3 is here, center of the well of three wells. Now, I mean, see here, now that, I mean, that distance from the common center of gravity, we have to find it out now. Common center of gravity, we have to find it now. Now, 25 minus 12.5. We know this 25 minus 12.5. I mean, this is, what is this? At which distance? Now, I erase this of the component. You might have been understood. Now, I'd like to take, this is 50. My CG is here. Then CG, I mean GG1 or GG2. GG1 is this, GG2 is this one. GG2, GG1 here. Now, what is the distance? Now, this is given 12.5. What is the distance? What is the distance? Sorry, I've done small mistake. Okay, now I mean, based on that, we are finding our CG1. I mean, anyway, this is Y bar we know very well, 50, but 25 minus 12.5. 25 minus 12.5. I did a small mistake here. This is not 50. This is 25. 25 minus 12.5. This is going to get CG1 and CG2 because both are symmetrical well. And this is our R1, R2. Now what is R3? R3 is vertical weld. This is we can directly taking from the CG 12.5. 12.5. Now go for our moment of inertia calculation. J1 is equal to J2. I mean L1 squared divided by L2 12. Sorry, L1 squared divided by 12 plus R1 squared. We already know that this is in the derivation. Substitute directly, then you are going to get this value. Now see here J3. J1, J2 is equal. J3 is L3 squared. L3 squared is 100. A3 is nothing but A3 is nothing but 100 into T. L3 is 100 squared divided by 12 into 12.5 square. 12.5 square. This is our J3. Now 2J1 because this is a 2J1. J1 is equal to J2. Now J1 plus J2 nothing but 2J1 or 2J2 plus J3. This is our common moment of inertia with respect to center of gravity CG for all the welds. This is our J value. Then go for the finding tau 2. We know that moment P into E, right? P into E we already found it this. P into E, this one. 11,250 into 10 power 3. Now we know that R value is 62.5. 62.5. Then find out this divided by 30. Denominator is our J value. J value. Then find it out. Okay. J value. This is our tau 2. Tau 2. R value already we have found it. Okay. Now J value we have found it now. We know that in terms of tau 2 in terms of T now. Now tau 2 in terms of T. Now tau is I am taking this bottom weld. For example, I am taking any one of the weld here. This is my tau. This is my tau 2. Now earlier weld is both are identical. The distance also equal. 50 mm length of the weld. Vertical distance between the weld is 50 mm. Hence, we directly used A, so square root of A into A. Earlier case, I am talking about tau 2 is equal to square root of A squared plus A squared. Horizontal component, vertical component was same because of symmetrical weld, symmetrical distance. Earlier case, but this case the angle is given. Angle we have found. We have to use that to find out our vertical component vertical shear stress component, horizontal shear stress component here. This is the thing we have found tau 2. Tau 2. Now what is this tau? Tau 2 horizontal component. Horizontal component with respect to tau 2. What is horizontal component with respect to tau 2? Then tau 2 into sine theta, vertical component, this one. Tau 2 into cos theta, tau 2 into cos theta. This is horizontal component now. Because that tau 2 at which angle is acting, we came to know that 36.87. Our tau 2 is acting which angle? 36.87. We have found it this. Okay. Now tau 2 vertical component. Vertical component with respect to tau 2. Horizontal component with respect to tau 2. This one. Now this is a direct shear. 300 by T. 300 by T is a direct shear here. 300 by T is a direct shear here. Right? Now add it. That's all. Whatever we discussed earlier problem, it's the same concept now. This tau 1 plus this vertical component. Both are vertical. Then add it. 1094 plus 300. 1394 vertical component. Horizontal component is as it is 1459. Now go for finding the common resultants here. Then common resultants here, take this one to, common resultants here, tau is equal to square root of 1394 squared plus 1459 squared. You are going to get common resultants here. Common resultants here, or else you may say that design resultants here. This is going to be used for finding our thickness of the weld. Now, these are the calculations I told you already. Now come to this. Now this is our common resultants here. Now, our permissible stress is given, CS is given. Then now we know this common resultants here. Equate both. You are going to find out our thickness of the weld. Now thickness of the weld is this one, 20.19 mm. Thickness of the weld is 29.1 mm. This is the leg length, 28.56 mm. Okay, this is very important. Thickness of the weld is very, very important. Now I come to the next problem. These are all very similar. Very fast manner we discussed. If you have any doubt, please go ahead. I explain you further also. Now see here, an eccentrically loaded bracket is welded to the support as shown in figure 8. This figure. Now the load is a 25 kilonewton acting eccentric distance 100 mm. Okay, the permissible shear stress for the weld is 55 Newton per mm squared. Load is static condition. Determine the throat and leg dimension for the welds. Now this weld is same. This problem is same as well as earlier problem. Now earlier problem we have discussed, these two welds are identical. Vertical welds are identical. Earlier problem, vertical welds are identical. W1 and W2 are identical and symmetric. This weld is horizontal. Horizontal weld. This horizontal weld. Horizontal welds are identical. W1, W2. Vertical weld W3. Now this case, vertical welds are identical. I am considering W1, W2. This one. This is our horizontal weld is not identical with respect to our vertical weld, because vertical weld W1, W2 lengths are same, but horizontal weld W3 is 100 mm length. Vertical welds lengths are 150 mm length. They have given now. Now the same approach. Earlier case, horizontal welds are identical. Then Y bar was same. Finding Y bar was very easy. Earlier case. Now nothing but this distance between two welds 100 divided by 2. Now here horizontal welds. Here vertical weld. Horizontal vertical welds are same. Here horizontal welds are same. Then vertical distance between the weld is 100 mm. Hence this is our Y bar. Now in this case, vertical welds are same. What is the horizontal? What is the X bar here? In this case, the X bar is very easy to find it out. 100 divided by 2. This dimension divided by 2. Then that is our X bar. Because W1, W2 symmetry. Distance between these W1, W2 100. I can easily find out X bar. Then Y bar apply earlier concept. Y bar is nothing but 150 for one weld, 150 into 150 by 2. The another vertical 150 by 150 into 150 by 2 75 mm. Then horizontal weld is here. I am assuming thickness. Center of gravity 0. 100 into 0. Then this is going to give your X bar, Y bar. Similar concept. Then A1, A2, weld A1, area of weld A1, area of A2, area of A3. Then go for total weld area. Now find out the total. Direct shear, primary shear. Once you find out the primary shear, go for the secondary shear. The secondary shear, we should know the distance. At what is the farmost distance the weld is presented with respect to center of gravity. Now, what is the farthest distance? See here, this is our center of gravity. Now, this is X bar, we know, right? X bar is 50 mm. x bar 50 and y bar is equal to what we have found. Y bar is 56 2.2 mm. Now go for this. This is now y bar is 56. Here y bar is 56. What is the total length of the weld, vertical weld length? 150. Then what is this distance now? I mean 150 minus 56.25 plus horizontal distance is nothing but this one divided by 2. Now we are able to know that what is R. What is the farmost distance from the center of gravity? Then this is 106.25. What is the angle? At which angle, at which inclination secondary shear is acting? That we have to find it out now. Then theta minus 90. Then this is the angle. Okay. Now tau 2. At which angle tau 2 is acting with respect to horizontal axis? Now tau 2 is, that is 27.08 degree. Now come to eccentric distance. We know now this is a distance given 100 mm. The eccentric distance is now x bar is here. Now here this distance is 50. Then 150. Then find out the moment here. Now go for the moment of inertia calculation with respect to each weld. Moment of inertia calculation with respect to each weld. Now I am considering weld G1 and G1 G2 identical. Hence, with respect to center of gravity, common center of gravity G1 is equal to G2. Now this is similar whatever we discussed earlier, same way. Now this is 75. This is 75 is vertical distance here. Now 56.5 is our y bar. Then at which location y bar, and 75 minus 56.5. Earlier I discussed in the earlier problem. Here x bar, how I discussed x bar here, 25 minus 12.5. This is a 12.5 here. Similarly, we are considering here now 56.5. Now this is now, CG. This is what is the distance? This is nothing but, for example, I am telling this is nothing but 75. Now our y bar, where it is sitting? Y bar is sitting here. 56. Then we are considering this 56 minus with respect to CG1 or CG2. Then 75 minus 56.25 whole squared plus 50 squared. Horizontal distance is both 50 x. Then this is our 53.4 mm. Then this is R1, R2. R1 is equal to R2. Then similarly go for R3. R3 is very simple. R3 is nothing but y bar. Nothing but y bar. Then you can find out J1, J2 are identical. Then both are equal. Then J3 is with respect to weld 3. This weld CG3. GG3 now with respect to the GG3, A3 into L squared by 12 plus R3 squared. And finally, total moment of inertia with respect to all 2J1 is nothing but J1 plus J2. Okay, J1 is equal to J2, hence 2J1 or 2J2 plus J3. This is our total moment of inertia. Now go for the tau 2 calculation, shear stress calculation, secondary shear stress calculation. We know M is nothing but moment, P into E. Then now here R is we know, this is the farthest distance, R is we know. Then find out your tau 2. Now tau 2 is this one. Now tau 2 is acting, which angle of inclination is tau 2 is acting now? Tau 2 is acting which angle of inclination? 28.7. Then find out the tau 2 is resolved into two components. We are finding directly tau 2 like this. Now the tau 2 is resolved into two components. One is horizontal components, another one is vertical components. Then 219.2 into cos 28.7 horizontal components, 219.2 into sin 28 vertical component. The vertical component is directly due to direct shear. Then add these two components. This is the new vertical component. This is a total vertical component of shear. 165.64 by T. This is the horizontal component. Now we go for the common resultants here or design resultants here. Now this is now tau is equal to, now this is the common resultants here, I mean, or resultants here for design. Now tau is equal to vertical component squared plus horizontal component squared. Then you are going to find out this is our tau resultant, common tau resultant. Now use these relations already given this tau is here permissible, then we are able to find out what is the thickness of the weld. What is the thickness of the weld? T is equal to 4.63 mm. Then leg length also we are able to find out. Okay, leg length also we are able to find out. I mean, this is the our leg length. This is leg length. This is our weld length. This is our right. Where is our T? T is here. T is sitting here. Okay, so I hope that you might have been understood that. Okay, now I stop here. Now we go to, if you have any doubt, please. You have any doubt? Just we start the springs today. Yeah, please guys, any doubt? Hello? Yeah, Abhilas, you are put to 25. What is this? I'm not getting. Abhilas Reddy, are you there in the meeting? Yeah, please, guys, any doubt? Hello?
No, sir.
Okay, Amarnath, thank you. Okay, I go to springs. Just we start springs at least. Yeah. See, you might have been seen springs. I mean, everyone we played with the toys, right? In our childhood age, right? Then there are so many springs in different types of springs they are using in the toys to store the energy, to release the energy, right? While apply the force in the spring, it will be stored energy in the toys. I mean, the mechanism in the spring mechanism. When you leave the apply the load, when you leave the applied load, the toys moving, right? Because once you applied the force, the spring toys absorb the energy. When you are leaving the load, the toys is moving because of the energy released by spring. During that time, the toys is moving, right? So anyway, there are a lot of applications. The application of spring is not limited at all. Okay, well, we will see the catalyst type of springs. Yes, spring is defined as an elastic machine element which deflects under the action of the load, right, and returns to its original shape when the load is removed, right? It's a very simple mechanism. Take one simple spring, compress it, then after compressing, leave your hand, then what will happen? The spring come to original shape because of absorbed energy now released. Then everything should be happen within the elastic limit. Then only the spring come to again original shape. If you go plastic deformation, the spring will not come back to original shape. Okay, that is very important. Now, applications of spring. I mean, just I tell you some common things. The springs are used to absorb the shock. I mean, absorb the shock and vibrations. You know very well. Vehicles, for example, vehicle suspension springs, railways buffer springs, also buffer springs in elevators. And another example application, springs we are using for storing the energy. I mean, it's example for clocks, and also in toys, moving elements, and circuit breakers. These are the examples. and the springs can be used for measure the weight. In weighing balance, people are using springs. Okay. In weighing balance, people are using springs. And springs also, when you apply the force, we can control the motion also. And especially in mechanical, IC engines, springs we are using in cam and follower mechanism to maintain the contact distance between the two elements. Okay. Also in springs we are using valve activating mechanism. The spring is used to, valve acting mechanism, the spring is used to return the rack ram to the normal position. Okay, these are the applications. The application of the spring is not limited. There are huge, we cannot limit. It's a lot of applications, hence we are considering in our subject. Okay, now springs can be classified based on their shape. Springs can be classified based on the shape. For example, the most popular spring is helical spring. These are the helical spring, most popular type spring. Okay, the most popular spring is helical spring. The helical spring, how we are doing this, how we are making to form the helical shape from the bare wire, which is bent in the form of helix. Okay, that way only we are making helical spring. Okay, the helical spring can be we again classified into compression spring and tension spring. This is spring. See, the first one is compression spring, the second one is extension spring. When you apply the load, the spring is going to be compression. When you apply the load, the spring is going to be extension, right? The spring 2, we cannot apply compression load because each turns of the spring is already compressed. Even if you apply compressed load, what will happen? The spring is going to be plastic deformation. The spring going to be distorted. Hence, only in this compression spring, only in this spring we can apply the tensile load. This spring, in this spring we can apply the compressive load. Okay, that's what this helical spring can be classified as a compression spring and extension spring. Right now, this is the what type of failure here occur? Please generally you tell me that now. What type of, in general way, you tell me that what type of failure will occur in this spring if apply the load? I give you a clue, then based on that you tell. What is the tensile load? In general, what is the tensile load? The bar is subjected to this. Now you tell me. This is tensile load. Suppose the force towards inward direction. Both.
Sir, hello, sir.
Yes.
Sir, time up, sir. We have another class.
Okay, I stop it here. What type of force now? What type of failure now? The spring subjected to this load. What type of failure? Please tell me that. I can close the meeting.
Tensile failure.
No, pa. See, here, this is
Shear failure, sir.
what, pa?
Shear failure.
Shear only, exactly. See, this is the axis of the spring. This is a not axis of the wire. That's what I put. This you consider. This is a bare wire. Bare wire. This is the axis of the wire and the loads are symmetric. Hence, the object going to be subjected to tensile or else compressive. But in this case, whatever a load will be acting, the load is axis of the wire? Not. It is axis of the spring. And the load is offsetted. Hence, each turn of the spring going to have a shear only. Each turns of the spring going to have shear only, not tensile. Please, very important. This kind of question you may expect any interview or even objective type or competitive exam. So the compression and the tensile spring not subjected to tensile stress or compressive stress. Both springs are subjected into torsional shear. Torsional shear. Okay. So these remaining things we will discuss in the next class. I mean, terminology. The next class, I mean, we are going to know 2 more class, right, Kalyan? Kalyan.
Yes, sir. On
In
Monday
the 2 more Monday class,
and
I'm going
Tuesday.
to take 1.5 hour, and Tuesday class I'm going to take 1.5 hour. So we can complete. Then if it is remaining things, I hope that we can complete within 3 hours. Still, if you are going to have some more content, then I tell you how to study. You go ahead with it, self study. I mean, maybe slight, very small content you may do self study. Most of the things I try to cover in the next couple of classes. Okay. Okay, guys, I come to this. Yeah, if you have any doubt, please go ahead. Yeah, Dilip, tell me, Dilip, you raised hand. Dilip.
No doubt, sir.
Okay. Yeah. Okay. Shall I close the meeting? I'm closing meeting, Kalyan.
Yes, sir.